Good day everyone, today I'll be discussing the vertical electric generator. Who invented it, what problem it solved, and how it changed the life forever. This invention made a turning point in human history, powering the world we know today. Who came up with the idea first? The first person to successfully create an electric generator was Michael Faraday in 1831. He invented the Faraday disc, which used electromagnetic induction to generate electricity. And just a year later, Hippolyte Pixii developed an early alternating current generator. Later, between 1866 and 1867, Siemens, Whetstone, and Barley improves these designs, creating industrial dynamos capable of generating larger amounts of electricity. These were crucial for practical and commercial use. What problem it was trying to solve? Before generators, factories relied on steam engines and built to run machinery. These were inefficient, polluting, and limited to local operations.
Mechanical energy can be converted to electrical energy.
This means industries could have a cleaner and more efficient and more reliable source of power to run machines and tools. What is life before the generator? Life before generator was tough, especially in industrial settings. Factory ran on steam power or water wheels. These methods were loud, dirty, and dangerous, filling cities with smoke and soot. Electricity existed only in laboratories and experiments. The invention of the generator brought the world into a new era of technology and progress.
This is the part 2. Scientific principle of a generator. In 1831, Michael Faraday stumbled upon electromagnetic induction by accident. While passing a current through a wire near a compass, he noticed that the compass suddenly moved. This groundbreaking discovery revealed that flowing current through a wire generates a magnetic field. By reversing the process, Faraday found that it creates a voltage and current flow when connected to a load. This discovery paved the way for generating electricity from one source to another. How an AC generator works. This is how a basic AC generator works. It has two main parts, the stator and the rotor. As we know from earlier, moving a coil on a magnet or a magnet on a coil produces electricity. As the coil rotates within the magnetic field, it creates a changing magnetic flux, which produces an alternating current. The electric current by the generator is driven by an electromotive force, which is also known as voltage. The induced voltage is directly proportional to the rate at which magnetic field lines are cut by the conductor, which is you can see here. As you make it faster, the lights get brighter.
Good day everyone, today I'll be presenting an analysis of AC and DC generators. We'll take a deep dive into their parts, understand how they work, and see how these components play vital roles in generating electricity. This presentation is entitled Unveiling the Powerhouses, AC and DC Generators. Generators operate on Faraday's law of electromagnetic induction. This principle states that an electromotive force or voltage is generated when a conductor cuts through or is exposed to a changing magnetic field. Electricity is produced through the dynamic interaction of magnetic field and conductors, where mechanical energy from a prime mover is transformed into electrical energy. In AC generators, key parts include the magnetic field source, the armature, slip rings, and brushes. The prime mover rotates the shaft, creating motion that leads to induction. For DC generators, a commutator replaces slip rings, ensuring AC is rectified into DC. Supporting components like the yoke and poles provide structure and enhance magnetic paths. Together, these parts enable the conversion of mechanical energy into electrical energy. An AC generator is built around the two main sections, the stator and the rotor. The stator is the stationary part with windings where voltage is induced. The rotor spins inside, producing a changing magnetic flux. Slip rings connect the rotating parts to the external circuit, while brushes transfer the alternating current. Finally, the prime mover such as turbine or engine drives the rotation needed to start the process. Each component of an AC generator is indispensable. The stator induces voltage, while the rotor provides the magnetic field. Slip rings ensures continuous AC transfer, and brushes collect this current for external use. The prime mover supplies the initial mechanical input, setting everything into motion. Together, these components form an integrated system where energy flows from mechanical rotation to usable electrical power. Now let's take a look at DC generator. The armature is the rotating part where EMF is induced. The field magnets create the necessary magnetic field. Instead of slip rings, a commutator is used. This mechanical rectifier cleverly converts the internally or generated AC into DC. Brushes then collect this rectified current and transfer it outward. Once again, the prime mover supplies the rotation to drive the process. In a DC generator, every part serves a unique function. The field magnets provide a steady magnetic field. The armature generates EMF, and the commutator ensures the current output is direct, not alternating. Brushes act as collectors, while the prime movers provides the rotational energy. The synergy of these parts guarantees that generator delivers a consistent direct current output. Both AC and DC generators rely on electromagnetic induction and share components like the armature, magnetic field system, and brushes. However, their key difference lies in output collection. AC generator uses slip rings to transfer alternating current directly. DC generators, on the other hand, use a commutator to mechanically rectify AC into DC. This distinction defines their applications and the type of current they supply.
Evolution of generators. The principle of generator began in the 1820s when Michael Faraday and Joseph Henry discovered the electromagnetic induction, or also known as Faraday's law. This principle states that a moving conductor within a magnetic field produces or induces a voltage. This discovery paved the way for various experiments and eventually led to the creation of devices such as the generator, Faraday's electric generator. In 1831, because Faraday discovered the principle of electromagnetic induction, he was also able to create the very first generator, called the Faraday's disc. This generator produced a continuous electric current, specifically direct current, or DC. This device was composed of a copper disc, brushes, and a permanent magnet. It was operated manually with a handle attached to its construction for turning. While it did work, this model of generator produced a constant but very weak current, early dynamo. In 1832, a French inventor named Hippolyte Pixii created a generator called dynamo, which was based on Faraday's discoveries and experiments. His invention introduced the term dynamo. The purpose of dynamo was to convert mechanical energy into a direct current. The device still used a U-shaped permanent magnet, but Pixii added fixed coils around which the magnet would rotate. However, during testing, Pixii discovered that the current kept changing direction depending on the rotation of the magnet. In reality, he had already produced an alternating current, or AC. But since AC had not yet been well studied at that time, he thought there was something wrong with his invention. To address this, Pixii consulted the electrician Andre Ampere, who suggested adding a commutator, which Pixii has followed. And as a result, the current flowed in only one direction. However, it was pulsating DC or not continuous. This generator was successfully used for some applications and was relatively large in design, making it suitable for laboratory experiments. However, it was not practical for telegraphs, which were the main communication device of that era. Because of this limitation, Pixii's generator was labeled as inefficient for widespread use. Dynamo era. After the invention of Pixii, the dynamo became the primary type of generator used. In 1860, Antonio Pasinotti created a dynamo capable of producing continuous direct current for the first time. His invention featured a ring-shaped armature which rotated within multiple windings of coils. This design enhanced the magnetic field strength, allowing the dynamo to generate a larger and more stable DC output. And next, still within the dynamo era, in 1867, Werner von Siemens and Charles Whetstone developed the idea of creating a dynamo that could generate electricity using the generator itself. Instead of using a permanent magnet, they replaced it with electromagnet in the generator's construction. The concept was that the electricity produced by the generator would be fed back into the wires of the electromagnets. In turn, this current would generate magnetism, which could then produce more electricity, and then creating a continuous loop. This process is called self-excitation. This new feature of the dynamo greatly boosted the role of generators in society, as they could now be used for industrial applications. Next is the core input. In 1871, based on the idea of xenogram, an iron core was added to the magnetic field or magnet of the generator. This improvement allowed the magnetic flux to follow a more organized path instead of being scattered. The addition of the iron core made it possible to generate a more powerful and consistent DC output. This advancement also made the generator applicable to nearly all commercial uses, powering telegraphs, arc lamps, and even being used in factories. 5 years later, in 1876, Charles F. Brush further improved this type of dynamo, making it more efficient and reliable. Because of this, it became widely used by telegraph companies. And by 1878, the use of AC, or alternating current, and AC generators began to be implemented, pioneered by the Gans Company. And for 1880 to 1886, AC systems were further developed and applied to different uses. However, DC power and generators were still more widely used. This period also marked the beginning of the famous War of Currents, which pushed researchers to continue improving both systems. And in 1886, George Westinghouse and Nikola Tesla led the development of AC systems, and for the succeeding years, Nikola Tesla created the multi-phase AC generator, while other inventors developed polyphase AC generators, which is capable of controlling electric motors. And in the late 1880s to 1890s, the design of AC generators improved and spread widely, leading to more effective applications. One major advancement was the creation of the three-phase AC generator, which is still used today for power generation and distribution. The three-phase AC system made it possible to supply electricity to entire cities and power stations, something earlier generators could not achieve since they could only produce minimal amounts of power. Modern generators. Today's generators have evolved to various designs and applications. We have diesel and gas generators, which is commonly used for portable and backup power, nuclear power generators, which is utilized for driving steam turbines, renewable generators, which is designed for sustainable energy sources such as wind turbines, hydropower, geothermal, and others. Modern generators now come in different sizes. They are lighter, safer to use, and are integrated with advanced systems for control and stability. They are also more efficient, capable of supplying electricity on a large scale across different regions.
Possible evolution of generators in the future. What I think about this is the future evolution of generators towards greater efficiency. What am I seeing right now is permanent magnet synchronous machines. I think this will replace traditional alternators in the future. This type of machines is the current front runner, but what lies ahead in technology is still uncertain. This is a classic example of our technological evolution. New innovations emerge to overcome the limitations of older ones. One example for this are digital cameras. The digital camera replaced the film-type camera because digital camera has many advantages, and one of them is efficiency. Maybe we can see that also in electric generators, and I think the cycle of improvement is constant. So, what cutting technology today will likely be replaced by an even better technology in the future.